Welcome. In this video I'll discuss ion viscosity, and this comes in several different forms. There are the parallel viscosity, so along the magnetic field, and this is very similar to the viscosity in unmagnetized plasma. There's then perpendicular viscosity, which is the viscosity across the magnetic field, and this has to take into account the finite Lama radius. And then finally there's a gyro viscosity, which appears as if a perpendicular viscosity, but in fact is not relative viscosity in the same way, because whereas these first two are collisional, so these depend on the collision frequencies, so these are collisional. Those we'll see in different ways. So for example, this viscosity increases with increasing collision rates, whereas this decreases with increasing collision rates. But both these depend on collisional processes. This one is collisionless, so it doesn't depend on the collision rate. And in fact it's not really a viscosity in the same way as the other two, because it doesn't result in any dissipation, so there's no heating or dissipation in general due to this term. Okay, so first we'll start with the parallel viscosity, and we're going to build up essentially terms of involving in the stress tensor. So we have the pressure tensor, which we write in general as a combination of a scalar pressure, which is the trace of the pressure tensor, plus the stress tensor. So this is the identity. It's like delta alpha beta, for example. In tensor notation, so this would be p alpha beta. This is the diagonal, just one's on diagonal, and this is pi alpha beta. And so what we're talking about here is terms in this stress tensor here. And in general for collisional plasmas, so the Brzezinski model, for example, you split this stress tensor into 5 components. So it's the sum over 1 to 5 of these pi I components. And so the first ones, so pi naught, so I want to go from 0 to 4. Okay, so pi naught is the parallel component, so parallel viscosity. This is pi naught, which is, so this part here, this is the B, this is the unit vector along magnetic field. This is B field unit vector. You might recognize this as 1/3 times the identity matrix. This is essentially the compression term. If you always have a term which looks like diffusion, this will look like a parallel diffusion. And this is from the compression of the velocity, or compression of the fluid. If you write out these here with this double dot, is a contraction. So this has 2 indices. This is basically in tensor notation. This is the gradient in each direction alpha times u beta. So this is a rank 2 tensor here, and this is a double contraction. So this part here, this we can write as b alpha b beta minus 1/3, and then this is just the Kronecker delta alpha beta. And so this is this double dot here just means a contraction over both the alpha and beta indices between this tensor here and that tensor. And so if the magnetic field is straight, so if grad b is 0, then this term here with the b and 1/3 times the identity matrix contracted on grad u. So this is b dot grad, so contracting this b with that here gradient here, and then b dot of b dot u. So this is the parallel gradient of the parallel component of the velocity minus 1/3 times the divergence of u. So this is essentially the diffusion of the parallel, well, the divergence of this term will be the diffusion of the parallel velocity. So we can write this as basically grad parallel u parallel of the parallel gradient of the parallel velocity. And so in the fluid equation, when we have things like divergence of pi, so this will contain terms which are like eta naught. So I have a term which looks like eta naught, and then I have a parallel gradient from this divergence, and then here we have a parallel gradient of u parallel from this term here, i.e. it's a second derivative of the parallel velocity. So this is a diffusion. So it's diffusion of parallel momentum along B. And now if you write down this coefficient at the front, eta naught, this is the coefficient for this parallel viscosity. So eta naught is different for electrons and ions. So for ions, this is given by, so it has the ion collision time. Yes, this is 1 over nu I. So it's the collision time. So as collisions become more frequent, this gets smaller. Alternatively, if you go more and more collisionless, then this gets larger and larger. And similar for the electrons. So the electron term is, and so you can see as the collisions get more frequent, so as more collisional, then tau e goes down and this gets smaller. If there are fewer collisions, or so for example, if temperature goes up, so temperature increases, the collision time also increases, and so eta increases. You can kind of see that this is because if this is a parallel diffusion, if the ions can simply move along the field lines without colliding, then the momentum will spread very quickly along field lines. So if you have a field line like this equation is simply saying how fast, if I have a fluid element which is moving quickly here, how quickly does that momentum get transported over here? Now if it's collisionless, those ions can simply move directly from one to the other, or flow back and forwards. So you simply have ions which are moving back and forwards, and so the momentum essentially moves like the thermal speed, or a few times the thermal speed, along the field lines. Whereas if it has lots of collisions, then it takes longer for the momentum to diffuse. So that's parallel viscosity. The second components are perpendicular viscosities. And there are two parts to this, is pi 1 and pi 2. Where here this I perpendicular is the identity minus the parallel part, so it's the delta ij, so the perpendicular part, minus the parallel part, so minus bb. And this w is the rate of strain tensor. And this can be written in tensor notation as this is a tensor which is 0 under translation or rotation. So if the fluid element is just being rotated or moved as a solid body, so if you have a motion, so either translation or rotation as a solid body, then this is 0, and so it's just measuring deformation. So we have a stress tensor here. These are components which are perpendicular to the magnetic field. These dots are essentially contracting. These are all matrices, so rank 2 tensors, and this is a rank 2 tensor. This is contracting essentially one of these indices with this, and the other index with b, and you end up with an operator which is perpendicular. The forces are perpendicular to the magnetic field. And the coefficients in front, these are these eta 1, so for the ions is, and for the electrons. So you see these equations, these have tau, the collision time on the bottom, and so as the collision time gets larger, so as the temperature goes up, say, or collisions become less frequent, then this gets smaller. So this is the opposite trend to the parallel viscosity. Because this, in this viscosity, if there's no collisions, then there's no transfer of momentum. And so what we're talking about here is you have a magnetic field, you have particles which are moving on orbits, say ions. If there are collisions, then a nearby magnetic field, see both B fields here. So you have two particles, say colliding, so particles on different magnetic fields. These can collide or interact with each other, and transfer momentum from this field line to this one, but only if there are collisions. And so if the temperature goes up, this is essentially the Lam radius comes into here. So you have a thermal speed squared, and you have a cyclotron times. This basically gives a Lam radius. So as the Lam radius gets larger, this viscosity also gets larger because the momentum is transferred quicker. But as the collision frequency gets smaller, so the collision time gets longer, then this viscosity gets smaller. So it's basically the transfer of momentum across magnetic fields. And so it's smaller than parallel viscosity by at least the ratio of the Lam radius to the parallel length scale. So it's smaller than the parallel viscosity by the ratio of the square of the iron Lam radius to the parallel length scale. So I'll call it L parallel as like parallel length scale, all squared. You see this coming from here, the cyclotron frequency squared, and this will give a sound speed squared from the temperature. So this gives an Lam radius squared term. Okay, then finally we have the gyro viscosity terms, and these are also perpendicular to the magnetic field. So it's perpendicular to the magnetic field, and it's also perpendicular to the strain. So it's perpendicular to the direction where the plasma is moving, and this means that there's effectively no work done. And this means that there's no dissipation, there's no dissipative heating or viscous heating. So the coefficients in front is eta 3. So this coefficient here for the ions and electrons. So for ions and for electrons, you have a similar thing. So in this case, it has actually the opposite sign for the electrons. But in both cases, it doesn't depend on the collision frequency. So it doesn't depend on tau, E, or nu, E or I. So no collision frequency dependence. So the origin of this is not in collisions. It's a collisionless effect, but it's in the orbits of the particles. Essentially the same physics as the diamagnetic drift. I'll see shortly. So it's effectively if you have a B field, so into the page, so we have iron orbits around like this. So you have same magnetic fields like this, and you have a gradient. So let's say I have a gradient of pressure in this direction. So these particles here are moving faster, or there are more of them. You end up with a net drift. So let's say if the particles are like this. So you have a net fluid drift downwards, which is the diamagnetic drift. So the fluid velocity is downwards, but there's no momentum transfer downwards because, of course, these particles are not actually moving. The particles are just going around in their orbits. And so what this stress tensor does is mostly cancel these to lowest order. This stress tensor term cancels the motion of momentum due to the diamagnetic drift. So this is called the gyroviscous cancellation, and it appears in many different forms. So particularly in reduced MHD, there are many different ways this appears. So there's gyroviscous cancellation. And this effectively says that the diamagnetic drift, so it's called U star, the direction of the momentum by the diamagnetic drift is roughly cancelled by the divergence of this pressure from the gyro terms. So pi g, I'm just calling pi g here is these two terms together, so pi 3 plus pi 4, these gyroviscous terms. So the cancellation isn't exact, but it's pretty good, and it's often assumed in many models. And so in the fluid equations, what you do is essentially you cancel these two terms. So in the momentum equation, you have something like this. We have a rho from here, and then here you usually have a velocity. But what you can do is just subtract the diamagnetic velocity. So instead of having the full u here, you subtract out this term, and on the right hand side you have the usual j cross b and grad p and so on. So I have j cross b, and then here you have the rest of the stress tensor, but you've already taken into account the gyroviscous stress. So this is one way of taking into account this gyroviscosity, and the physics is essentially this advection of momentum by the diametric drift and cancelling out that term. And so you end up with a term in the viscosity tensor. And clearly this is quite complicated. The cancellation isn't exact, but if you want to implement this in a calculation or in a code, clearly it's much easier to just cancel out the diametric drift here. So this velocity is quite easy to calculate, so it's quite easy to include this term by just including this bit here, rather than try to include the full gyroviscous stress tensor in here. As this is what's often done, although it's not an exact cancellation.